thank you, Fatma, for preparing that. So when I was in Munich, I stopped there, and Farzin also were at the chair of Robert? Robert? No. I just introduced you by describing that you joined also. Janis and I organized something what was called Quantum Breakfast every month. And since at that time Farzin was also in Munich, he joined a lot of times, and he also gave good contributions and good questions and a lot of discussions. Furthermore, he joined also this conference we gave for Ning, so we discussed about that just before. And in 2023, we gave a conference in memory of Ning Chai, who unfortunately died, and also there he gave a presentation and a lot of discussions. And I think also this paper is somehow based on this, as I learned. Now he's at the University of Waterloo, and today he will talk about three receiver quantum broadcast channel with quantum non-unique decoding. So the stage is yours.
Thanks so much, Christian, for the nice introduction, and thanks so much for the organizer for inviting me. I'm going to present my joint work with Patrick Hayden and Masahito Hayashi. I have quite a few affiliations. First of all, I am with the University of Waterloo, IQC, and also Pre-Maternal Institute, and also Free University of Ireland. How this happened, my US visa was not successful. I was going to start with a position with Patrick Hayden at Stanford last May, and it didn't go through, so I ended up in Canada with so many affiliations. The paper appeared published already in Analytic Conqueror about like a month or two, month and a half ago. So I'm going to talk about three receiver broadcast channels and introduce something called non-unique decoding, quantum non-unique decoding. Broadcast channels introduced by Tom Cover over 50 decades ago. Their capacity is not known, right? And they are generalized to quantum case. Later on, one of the authors in this paper also is my co-author. So what's the capacity of the quantum broadcast channel, of course, are not known because the classical setting also is not settled. But what is possible, how we can communicate over quantum broadcast channels? Let me start with CQ broadcast channel. This is a classical quantum broadcast channel. The inputs are letters. This is classical. The outputs, this is upon sending X over the channel, Bob1 obtains a density matrix, Bob2 obtains another density matrix. The goal is to send one message M1 to B1 and the second message M2 to B2. These two messages are individualized or private. Private doesn't mean that they are confidential. They are just individualized. Each receiver is interested in its own message. So there is nothing wrong if M2 is leaked. We don't discuss secrecy. There is no secrecy requirement. What is achievable? What coding strategies we can use to communicate over this channel? So we are going to be looking into a rate region for receiver 1 and receiver 2, or Bob1 and Bob2. One naive way is just to send information to Bob1. And we will get this whole level information here. Send nothing to the second receiver. The second time, this other thing that we can do is just send information to the second receiver and nothing to the one. And of course, we can do time sharing, the old trick in quantum, in information theory. But this is naive, this is far from optimal, of course. But over the years, people have developed more coding schemes in classical information theory, and they have been generalized to some extent to quantum. One thing that was introduced by Tom Cover already was superposition coding. There are two ingredients. One is superposition coding. The other one is Marton's code. Superposition coding is generalized to quantum setting in a straightforward way. The encoding is fine. The decoder could be problematic. But Marton's coding was quite challenging to be generalized to quantum setting. So there's a story that Mark Wilde says. When Mark was a postdoc at McGill, he introduced the first decoding for the Marton's code, and they published the paper in ISIT. But later, Paranov discovered some errors in the paper. Paranov mentioned those errors to Andreas Winter. Andreas Winter relayed them back to Mark Wilde. Mark fixed some problems in the paper, but there was a major issue still remaining. Pernopsen later published a paper. He introduced the idea of overcounting and kind of settled the problem in one-shot setting. And later, Mark Wilde fixed his paper and published the paper in IT Transactions. In this work that I'm presenting, we were not looking to settle Marton's code or find a simple solution for Marton's code. It just came out as a byproduct. And also, the idea of overcounting is so complicated, and also it applies to the easiest case of Marton's code. Marton's code and superposition code, as you probably know, are using as gadgets in more sophisticated coding schemes. Overcounting cannot be used there. Anyways, that was not the goal of this work, but it just came out as a byproduct. But let's go beyond the two-receiver broadcast channel and look into three-receiver broadcast channels. Everything is classical here, right? There are three receivers. There are three messages, one message for receiver 1, receiver 2, and receiver 3. The capacity of this channel is, of course, not known because the capacity of the two-receiver channel is still open. But we asked the question, are there special cases of this channel where the capacity is actually known? The answer is yes. The multi-level two-receiver broadcast channel, the capacity of this channel is known. What's happening here? First of all, we don't have three messages. We only have two messages. There's a common message M0, which goes there's a common message M0, which goes to all three receivers. And there is another message M1, which goes only to the first receiver. And the second receiver is degraded with respect to the first receiver. Degraded means that there exists a channel that if we concatenate with the first receiver, we obtain the output of the second receiver. This is degradable. For this, the capacity is known, established by El-Gamal and Chia. To obtain this capacity region, El-Gamal and Chia introduced the idea of non-unique or indirect decoding. And we thought how we are going to be able to do that quantumally, because, as I will explain shortly, it is in classical information theory. Classical information theory can deal with that kind of on the fly so easily. Let's go forward and see what is non-unique decoding. So in non-unique decoding, a receiver tries to decode a message that is not meant for that receiver, but declares no error if the decoding was not successful. In other words, the receiver gives it a shot. If it was successful, if it works out, good for the receiver. If not, no one really cares. That is the idea of non-unique decoding. So as I said, the tools of classical channel theory is able to deal with that easily, but quantumally, not really. And later we figured out that the problem with Marton code was something similar. To study that, to kind of develop that kind of non-unique decoding, we looked into the three-receiver classical quantum broadcast channel. Now there's a letter X. There are three receivers. We assume the second receiver is degradable with respect to the first receiver. There are two messages, M0 to all three receivers, and M1 only to the first receiver. It is reasonable to study this setting because the classical counterpart is already settled. That's why we are looking into this setting. But before there, let me just briefly explain what's happening in the classical setting. I manipulated my slides from half an hour to 20 minutes, so I don't know. I will try to be in 20 minutes. I don't know where I should stop somewhere probably, but I'm still trying to. Let's look into this totally classical setting, the coding scheme. We come and we split the message M1 into two parts, right? We generate a code book. This is superposition coding, and this is superposition coding different from the superposition in the context of entanglement that just discussed. Superposition coding is something totally different. In the superposition coding, we generate a code book to encode the first message, M0, the common message. On top of that, we generate another codebook to accommodate the message M10, yet another codebook to accommodate M11. We have 3 layers of code. These little black dots, they are my code words. Assume I send 111 one of these messages over the channel. The message that I choose to send is 111. This is just an assumption. And we want to write the error analysis. Any first course in classical information theory tells us how to use packing lemma to address these questions. We just write our messages and we look into all the induced distributions. I said that we send 111. If this was the case, there is no error. Whenever I have a star, that means that that message was not decoded successfully. Here in the second line, I assume the first message and second message were successfully decoded, not the third one. Here I am fine, but not here. To address that, I need to introduce by packing lemma a condition like this one. If I look into this third line, I need to introduce a condition like this from packing lemma. These are standard tools in channel theory. And for the last 3 lines, it means that if this codebook is not decoded correctly, the other ones are automatically gone. The induced distribution is the same. I get this condition. This is just warm-up. There is nothing non-unique here. But non-unique decoding comes when I am looking into the third receiver. Just one sentence, the second receiver doesn't need to do non-unique decoding. Why? Because it doesn't need to. If the Y3, the third receiver, just does normal decoding and looks into this codebook to decode the message M0 because it is all the receiver wants to get, we are not getting the optimal capacity region. Y3 needs to do non-unique decoding. What does it mean? It means that this Y3 tries to decode information encoded here plus information encoded here. But actually, the information encoded here is meaningful for the third receiver. So third receiver tries to decode whatever is here non-uniquely by looking into here. What happens if I induce all these scenarios? What happens? There is no error here. If this message is mistaken, this is correct. We do not declare an error. This is the key point. This is the first key point. So if this is, the receiver tries to decode this one. If cannot decode this one, that's fine. But here we have to declare an error. And we have this error term. If we put everything together, we obtain the capacity region. We had to do a little bit of Fourier motion elimination and we obtain the capacity region and we can find the matching converse. Let's do this quantumally. There's a reason why I listed this distribution because in order to be able to build the quantum POVM, I'm gonna be saying that I'm doing kind of equivalent to packing lemma. That's why I listed this. So in order to build a POVM, there are different ways of building these POVMs. I am gonna do this in one-shot setting. There are different tools. For example, we heard about convex splitting and position-based decoding. One can do that, but I'm doing pinching. This is how we do pinching. For any Hermitian operator with these distinct eigenvalues, we can define its eigenspace decomposition in this form. This is not a spectral decomposition. HIs are not necessarily rank 1. Their rank equals the multiplicity of that eigenvalue. By using this, I can define pinching map with respect to H in this form. For obvious reasons, this is a CPTP, this is a quantum channel. And one more notation for 2 Hermitian operators. If I write this eigenspace decomposition, this notation here means projection onto the non-negative subspace of T minus O. And one more thing from binary hypothesis testing, if I have 2 state rho and sigma, I want to distinguish them with this POVM where I define the POVM like this. I have pinched the second, I have pinched rho with respect to the eigenspace decomposition of sigma in this form. I can find this upper bound. First type error plus M, second type error is bounded in this form. This is Petrani entropy. This is known. Let's look into the quantum multi-level three-receiver broadcast channel. I already set the setting once again. M0 is supposed to go to all three receivers. M1 is only to first receiver. The third receiver needs to do non-unique decoding. What we did classically, and I'm just copying it here, we split message M1 in two parts. We built our codebook just like in the classical setting. In the classical, I said that there is a base distribution. We compare everything with respect to that one. Here, this state is my base state. If U fails, I have to compare this state with respect to this one. And the POVM that I have for that has this form. So I'm comparing this state with respect to this one, and I'm pinching this state with the spectral decomposition with eigenspace decomposition of this state, making sure that these two are commuting. The reason that I'm writing it this way to make sure that I'm making it concrete for people who are familiar with packing lemma, so that this can be used kind of counterpart to that. If V fails, I have to compare this state with this one, and I obtain another POVM in this form. And if X fails, I have to compare this with this. So the idea there, the point is that all these states are commuting, but also all three are commuting, so I can do simultaneous decoding. I have also worked with other tools like position-based decoding, convex split. This is much cleaner. Those are also clean, I'm not saying, but this is, this is, I believe this draws a much better line for people who are familiar with classical information theory. And finally, I want to make these are not code specific. In order to make them code specific, I develop my projectors, and I define this projector that I will use for building my POVM. This was for the first receiver. It was like a warm-up. Now the second receiver. As I said, the second receiver will try to decode this message also, although it is not intended for the third receiver. What happens is that if U fails, the decoder, the third receiver, declares an error. If this one fails, there is no error. So I need to only compare this state with this state. And I'm pinching this one with respect to eigenspace decomposition of this one, making sure that these two commute. That's not it. Kind of classical information theory already settles the matter here, but that's not enough for us. We need one more thing. In order to realize that non-uniqueness, I need to sum over all the sequences and inside each circle here. And if I do that, and I can use this operator to build my pretty good measurement and then upper bounded. So Christian mentioned something about Bielefeld, and when I was working on these things, realizing this correct projector, it was so difficult. I mean, I came up with a couple of things. I couldn't find the upper bound, and we were in Bielefeld. I talked to Masahito there, and I think it was the moment that we kind of realized the kind of correct POVM that gives us proper upper bound. And anyways, let me move forward. I think I'm omitting a little bit of these things. I'm not going to talk about them. If I have time, I'll come back to this. Okay. So we write this, if we continue with this POVM, we obtain the achievable rate region. This is my inner one. This looks exactly like the classical setting. I have replaced Y with B. Now systems B are quantum, and V, U, V, X, they make Markov chain. But in classical setting, this was optimal. I wrote the converse. It's the same. Right, the converse, people who work with the classical information theory, finding converse has to do with realization of these random variables U and V, and we should be so happy or not for finding a matching converse. It turns out that everything is the same. But here, I need to evaluate this region over this state. Here, U and V are generally quantum. They are not classical. And actually, when we write the converse, V depends on B1 and B3, U depends on B1. So U and V are generally quantum. Basically, this is tight only when B2, B1 and B3 are classical. But that is interesting because even if B2 is quantum, still we get that kind of additivity and we can find the matching converse. This is, there are some people who study this hybrid classical quantum wiretap channel. I have not looked into this precise matter so closely, but this is very interesting that when one of the systems is quantum, we still get additivity and we can find the capacity region. Let me move forward. So was this kind of non-unique decoding necessary? The answer is yes and no. I said that the decoder needs to look into part of the other message. That was necessary. Otherwise, we cannot get the capacity region. But what if the receiver tries to decode it uniquely? It turns out that if the receiver tries to decode it uniquely, we obtain a more complicated rate region. Its equivalence with the rate region of non-unique decoding is shown. So there is, at least in case of this three-receiver broadcast channel, there is no advantage of using non-unique decoding, but the reason that we claim, when we show that we know the converse, is that for the case with non-unique decoding, the rate region is simpler so that we can find the converse. If we do unique decoding, the rate region would be so complicated and maybe it is so difficult to find the converse. But it is generally open whether this non-unique decoding could give absolute advantage in other scenarios, especially involving POVMs and in quantum case. I think I have a slide for talking about Marton's code, why it becomes so tricky quantumally. But so we are quantum people. What motivated us to do this? What motivated us to study three-receiver broadcast channel? We want to send quantum information over broadcast channels. People talked about Igor Devetok's proof and also Andreas Winter together. So when Igor developed this paper, the paper which is credited for establishing the quantum capacity of a channel, there's a quantum channel. Everything is quantum. We want to send a quantum state from Alice to Bob. What Igor did, Igor said, let's consider sending a confidential message from Alice to Bob 1 and conceal it from Bob 2. We can make this coherent and we can find quantum capacity. This was the idea in Devetok's work. And I have replaced this channel with isometry. This is not general CPTP. This is isometry for some reason. Because when we send confidential message, okay, let me move forward. I will comment on that later on. But now we want to send quantum information over quantum broadcast channel. In order to send quantum information from Alice to Bob 1 and Bob 2, if we want to follow Igor Devetok's proof, we need to send classical messages, confidential classical messages to Bob 1 and Bob 2 and conceal them from Bob 3. If I manage to find the rate for transmitting of classical information from M to two receivers, conceal it from this one, we can make it coherent and we can get a rate for GHC distillation between A, B1 and B2. What's more, now I want to generate GHC state and EPR pairs. If I manage to send a message M1 confidential to B1, only to B1 and confidential from the 2, I can send an EPR pair I can generate EPR pair between A and B1. On top of that, if we manage to send a message M2 from Alice to Bob 1 and Bob 2, which is concealed from Bob 3, we can generate GHC between the three of them. This turns out to be 3 receiver broadcast channel with 2 receiver, 1 eavesdropper, or with 1 receiver, 2 eavesdroppers. Classically, extremely difficult. Achievability rate regions are scary, but we have done this. So this so there's a little bit of trick that exists here. Why I am changing this is the trick actually. Why I am changing the channel to an isometry. There might be some other people who can get the public information. But what's happening here is that when Alice tries to generate EPR pair with BOP1, EPR pair is concealed with rest of the word. That's why BOP2 is the environment or the outside universe after BOP1. That's why this is an isometry. And actually, we have actually done this work. This is not an archive, but this should be hopefully be out for ISIT for sure. A little bit of conclusion. The paper published in Henry Poincaré is like 70+ page paper. I only presented the simplest case here. We have 3 receiver broadcast channel with more complicated scenarios, sending different messages to different receivers. The technique that we developed here, this non-unique decoding, can be applied to scenarios for this compound channels with state. The people who have done those things, they have not used quantum non-unique decoding. I don't really know what they have done, but this kind of non-unique decoding can be useful there. And again, the question of whether this kind of non-unique decoding can give absolute advantage, that's also open to further investigation. And thank you.
Okay, yes, thank you. Are there questions or comments?
Thanks for the talk. So if I understand correctly, see this overcounting issue, right? I think that can be resolved much simpler. So I have worked on the situation, and
what can be resolved?
The overcounting, the non-unique decoding and the overcounting are kind of related, really, because the overcounting is essentially giving you an additional exponent which you're not able to kill in the error analysis.
That's true.
And there is a simple way to overcome that by so if you get an exponent at the denominator, you can kill that. So there's a simple way to do that actually, the overcounting issue. So I have seen.
I mean, what issue? I'm not.
So the overcounting that you presented in the beginning, right? You were talking about the Wills error and the Winters getting back to that. That's actually, you can resolve it in a very simple way.
Resolve what?
The overcounting,
you mean the overcounting is a difficult technique?
No, I know. The issue that resulted in the use of the overcounting technique, right? So there was a reason in the broadcast channel, that is, you're trying to, you have to pin down the message in the bin, in the actual code word in the bin. That is what is causing the additional exponent.
That's true.
In the error analysis.
That's true.
And to overcome that, you have this overcounting trick.
Right.
This can be resolved in a much simpler way.
It's already published. It's not in.
Yes, it's already published. So,
but it's not for the authors.
It's actually, we did it a long time ago in the classical setting. So in a classical setting, in another problem, we had the same issue where the exponent hits you, the probability of error goes
But the paper was classical information.
It is generalized also to the quantum setting. So I can talk to you about that. And so you can resolve this over this issue of the exponent hitting the probability of error, and the need for the overcounting can be completely pushed aside and solved in a much simpler way. And this also this question about so that's just one point.
So I mean, also overcounting has other issues. So I don't know. Right, or overcounting cannot accommodate common messages.
Yeah, overcounting, you can't use it everywhere and stuff like that. Yeah. The one more thing I wanted to point out is if you look at the non-unique decoding, right? I mean, if you see the Han Kobayashi paper in 1981 of the interference channel.
So Han Kobayashi did not use non-unique decoding.
No, so they did in the two-user interference.
So
It's
they
really
did
not
unique decoding, but you can also do non-unique decoding. Kobayashi.
I know. So you had this question about, does non-unique decoding ever strictly improve the achievable rate region? And I claim the answer to that is yes. Non-unique decoding can strictly improve. And a simple example is in the interference channel paper of Han and Kobayashi, where they look at an interference channel, they do non-unique decoding, and they plot the region in the Gaussian case, and they show that it appears we need to do non-unique decoding.
That's news to me because there is the IT paper by Shirin and others that show that
the Shirin and Vinod Prabhakaran.
Yes, right.
Yeah, I'm aware of that. So
it's not discussed there. I think they also discuss Han Kobayashi in that paper.
So we can talk of this offline.
Sure.
But
I love it to be true. I mean,
it's so we can discuss about it.
Sure. Thank you.
There are questions or comments. Yeah. That's one question.
Thank you for your fantastic talk.
Thank you.
When I was working on a position-based decoding for multiple access channel and security of quantum multiple access channel, I found a paper written by you and Fonolosa about how to calculate the capacity of a broadcast channel carrying simultaneously classical and quantum messages.
Yes.
I think the intuitions behind these two papers are the same, or at least there are many similarities between these two papers. You have reduced a 3-user broadcast channel to a simpler task, and you applied non-unit decoding, simultaneous non-unit decoding. From the additivity of classical capacity, we know that the capacity of this channel can be calculated by the additivity of classical capacity, because this first subchannel is a simple broadcast channel and the second one is a simple point-to-point channel. But the problem in the classical, even in the classical case, is that the capacity of the first subchannel is unknown in general case. So in the quantum setting, the problem is much more complicated. I cannot understand how you can claim that in this case the capacity is known, because you want to bypass the complexity of solving a quantum multiple hypothesis testing problem that is unsolvable in general case, yes? But in your case, it's solvable. But I cannot understand how we can calculate the capacity, since the capacity is still unknown in classical case.
I'm not sure I followed like the last minute. So maybe if probably write it down precisely, I should be, but it's not an M-array hypothesis testing. It's still, if you use position-based decoding, it will turn out to be binary hypothesis testing. It looks like M-array, it's not.